Okay, in the last video, we just finished all the concavity work here. Now, anything that is graphical in nature like this, you can check with your graphing calculator. Now, we may have to futz with the picture a little bit, but we should be able to make this check. So I'm going to put in my graphing calculator the original function, and eventually I'm going to remember to change the batteries. So putting in the original function, I'm going to put it in before we simplify it. So I put my entire numerator in parentheses, 10x cubed minus 25x squared plus 24x minus 8. My entire numerator in parentheses divided by my entire denominator in parentheses, 60x to the fifth. Now, one of the things that, points to doing all this work is that standard window, Zoom 6, that always works in college algebra, just isn't going to work on a lot of problems here. That there's what I see when I hit the standard window. Now, it does check a little bit for me, and we can see it right here. On the interval from negative infinity to 0, I'm supposed to be concave up, and we can see that right there. That the graph is going like that, and so in the second quadrant right here, we are concave up. So this first part checks, but our other parts of then down, up, up, we don't see that. It just looks down all the way here, and so we aren't getting the resolution we need on that standard window. And so in order to check this, we've got to give the calculator better numbers. And so we already know we've kind of already checked this part here, negative infinity to 0. It certainly looks concave up. And then we do get that change in concavity. It goes down at 0. But like we alluded to before, it changes concavity not because we passed through an inflection point, but that x equals 0 turned out to be an asymptote. So we've checked that first part, concave up, switching to concave down. So we really need to check this quadrant over here. And so giving it better numbers, notice that we can still see along the top here are x values. Now, we're not going to be able to give the calculator the best numbers here, because the best numbers are generated through finding the work with increasing, decreasing, local max, local min. Those are the best numbers. So we aren't going to be able to give it the best numbers, but we'll get good enough numbers based on what we have here. So we've already kind of checked this part here. So I'm going to start with my x-axis. I'm just going to start at -1, because we already know that this guy's okay. And then we got 0, 1, and 2. So maybe I'll go to 3. Just a little bit further than we need to. And I'll go ahead and count that off by 1s. Now, if we remember what the picture looked like, the part that we're checking, it was all right around the x-axis. So I really don't need to go up and down very much. So it was all right around the x-axis. And notice here, the y-coordinate I have is 1/60th. So what I'm going to choose for my y values is I'm going to try just doubling that. And so I'm going to go from -2/60, and notice I can just put -2/60 in there to 2/60. That I just took this y-coordinate I calculated and I doubled it. No point in counting off by 1s. Let's count by 1/60. And now graph. So it's going to take a while to do all those computations. And now we are seeing what we anticipated. Remember, we're just checking this part right here, that it should go down, up, up. And that's what I see, down and up. And then we said the inflection point should be at 1/1/60. Let's do a trace and go to x equal 1. So I put it in there, x equal 1, enter. And that does look like that's probably where I am changing from concave up to concave down. And then it gives me that coordinate there, and you could check that that coordinate is 1/60. And so this checks. We already checked over in the third quadrant there, that was concave up, and then it goes concave down to right where we got the blinking cursor, then concave up, and so it absolutely checks. And it also checks for us that we did not have an inflection point at 2. If I trace to 2, there's the point at 2, and it's clearly not changing concavity at 2. And so this absolutely checks. But the big point here, not only can you check, we couldn't do this checking until I knew this number. It was knowing this point right here, 1/160th, that allowed me to put the correct information in the calculator so I could see the picture. And so the calculus, yes, we have a graphing calculator. Why do all this? I couldn't make my graphing calculator give me the appropriate picture till I gave the calculator the right numbers. And that's why we're doing this. Yes, we have machines that graph much faster than we do, but they can't do a good job unless we give them the data upon which to work. And so that's why we do all this. So that guy checks. And again, I want to emphasize here, there will be a good number of you that when I say find the inflection points, you will get to this point right here and you will stop. You will find the possible inflection points, you will get that data, and you will just stop. And you will not make this chart. But as we've already seen, you've got to make the chart, because even though 2 was a possible inflection point, it didn't turn out to be an inflection point. So it's not good enough just to do the work to discover those numbers. You've got to make your concavity chart to show that you have an inflection point. Okay, so we will move on to the next problem. How to sketch polynomials. Put polynomials in quotation marks, because it's not just polynomials, and actually we're not even going to do a polynomial here. Non-fractions, things without asymptotes, and I just didn't know a good word for non-fractions, and so maybe I should have just left it non-fractions. But it's doing all the stuff that we've already done. You're going to do all your increasing, decreasing stuff. You're going to do all your concavity stuff. Then once I have once I've done all that work, I'm going to plot and label the points found. And what I mean, label each point to what it is. For example, if the point is a local maximum, you're going to write max beside it. If it's an inflection point, write IP beside it. That will help you when you go to actually draw the curve. Then working left to right, connect the points with the curve using the increasing, decreasing, and concavity charts as guides. And then C, check by graphing on your calculator using an appropriate window. The graphs should reasonably match. Now, they're not going to perfectly match because of the way we have spacing of tick marks and things like that, but they should reasonably match. So doing this first problem here, sketch the following, find the intervals where the function is increasing, decreasing, concave up, concave down, find all local extremes and inflection points. The original function, first and second derivatives are given. Come quiz or test time. If the derivatives are at all complicated, I'm going to give them to you. History has shown me that if I don't give you the derivatives, about a third of the class will calculate the derivatives wrong, and then I have to go through step by step, tracking all the errors all the way through the problem. So I will give you the derivatives in more complicated problems. But notice in the next problem we're doing, that's not particularly complicated, didn't give you the derivatives. Okay, so let's start this. Increasing, decreasing stuff. I already have the derivative, so I go to finding the critical numbers. So I set that derivative equal to 0 and solve. I can start this guy by factoring. I can factor out an x, e to the x, which leaves behind 2 plus x equals 0. That is now factored and equal to 0, so I can split it up. So I get one critical number right away, x equals 0. Here, we've looked at this before, but I'll look at it again. An exponential equation, take the natural log of both sides. Natural log of e to the x, natural logs and e's are inverses. And then this is going to happen every once in a while. Natural log of 0 is undefined, which just means there's no solution. It's not that I did bad work here, this is that this didn't lead to a critical number. And over here we get x equals -2. So there are my critical numbers, and then I'll just put a little note here. Note where f prime does not exist is not applicable. You don't have to write that down, but it is important that you think about if it's applicable, if it is applicable to actually use it, but it's not applicable, so I don't have to worry about that. Okay, got that information. Let's do my increasing, decreasing chart. And let's recall that my first derivative was 2x e to the x plus x squared e to the x, which I was able to factor to x e to the x 2 plus x. And you'll see why I like the factored version here momentarily. So making my increasing, decreasing chart with just my two critical numbers, 0 and -2. I have negative infinity to -2, -2 to 0, 0 to infinity. Test value. So -3, -1, and 1. And then I plug into the derivative. Now remember, all I need to know here is the sign. You can find the full value if you want, but all I really need is the sign. And so, since I have it factored right here, I can just plug into this factored version and see what I get. So if I plug -3 into the x, that's going to be negative. If I plug -3 into the e to the x, well, e to anything is positive. And if I plug the -3 into the 2 plus x, that's going to be negative. So I got a negative, positive, negative. The whole thing's going to be positive. That's all I need there. Plug my test value of -1 into this one, in here. If I plug into the x, it'll be negative. If I plug it in the e to the x, e to any exponent is positive, so I get positive. And if I plug into the 2 plus 1, that's going to be positive. And so that's going to be a negative there. And then lastly, plug in the 1. If I plug the 1 into the x, that's going to be positive. If I plug it into the e to the x, it's going to be positive. If I plug into the 2 plus x, it's going to be positive. And so the whole thing is positive. Now that's one way to do it. If you don't have the factored out version, you can just take your calculator, plug the number into the derivative, and see what you get. You can do it either way. If you choose to plug into the whole derivative, be sure you're careful with your calculations there. Getting these calculations wrong, just a tiny little error pressing up one button wrong, can blow the whole thing up. So be really careful. If you choose to plug into the full derivative, be careful. But once I have this chart, this tells me that f of x is increasing because the derivative is positive, decreasing because the derivative is negative, and back to increasing because the derivative is positive. And from here, I can say what's going on with my local extremes. And that's what we'll do in the next video.